So our next speaker is Ali Mesbah, actually one of my former colleagues back in TU Delft. Then he decided to move to Canada. Now he's with the University of British Columbia, and he's talking about software analysis for the web.
All right, thank you, Martin, for the introduction. The web has had a great impact on our lives. So from social to economic, even to software engineering. So today I'd like to talk about specifically not so much about software engineering in the broad sense, because I think that's just too broad, but more precisely about software analysis, because we're at Sainer, and Sainer is more of a software analysis conference. And I'd like to talk about some of the achievements, some of the challenges, and some of the future prospects that we might have in terms of how we as researchers could help maybe to mitigate some of the problems that we have. So before I delve into the challenges and the achievements, I'd like to take everyone through a very brief history of the web itself. So the web was proposed around 3 decades ago, and it was meant to be a very simple but elegant way of sharing documents for people, right? It was actually never meant at that point to be something that people would write full-fledged applications on. It was basically just, as I said, just for sharing documents between researchers. So it was elegant in the sense that there was the internet, of course, and this was a layer on top of the internet, and it made it easy through defining a set of standards for people to be able to go and retrieve a resource from a particular server anywhere on the internet, basically. So these were very static files. So you would have, for example, a file on a file system, and the server's job was basically just to retrieve that based on the request, and then send that whole static page to the browser or the client side, the browser in this sense. So the browser's job was basically just to get that page and show that to the user. There was not much processing going on inside the browser itself. So then, people saw the benefits, and then people, of course, started thinking, can we actually do a little bit better than just static pages? So then people wrote scripts, different languages were adopted on the server side to be able to actually generate these pages. So instead of having static pages, lying on the file system, people now were trying to write scripts that would generate these pages dynamically based on the request that was coming in, right? But it's still, if you look at the browser is still not doing much, right? So it just gets the generated HTML page as a static page, and then it tries to show that to the end user. Around the year 2000, Roy Fielding was a PhD student working with Rick Tyler, and then he proposed, together working with the W3C guys who actually adopt the standards for the web, he proposed an elegant architecture for the web, which is bound, which was called the REST style. And then this was interestingly also published at ICSI in the year 2000. Right? So this is maybe one of the very few examples of something that has been published at a software engineering conference and has had a tremendous impact in practice. Right? So what was the idea? The idea was for the server to be stateless. So that means basically maintaining no state on the server side, and that requires that every incoming request maintains or provides all the state information that is needed for the server to be able to understand, right? And of course, there was this notion of resources also proposed, so that the request would be going to a particular server and then getting a resource in a very standard and unified interface manner, right? So that was the basic idea. So this had a huge impact in terms of how the web actually became successful itself. But I mean, if I go back, if you still look at this elegant model, you still see that the browser is very inactive. It's not doing much, right? So there is no processing going on inside the browser. Of course, this meant, for people who still remember that, and maybe even nowadays, sometimes we see these websites, every time you click on something, the whole page goes blank. You have to wait, and then something comes back, and then the page refreshes that. So this is the traditional classical model of the multi-page paradigm for the web. So people saw that this was not really working. So then the next step was for people to add this kind of engine inside the browser. So of course, Sun tried to do this with applets. And that didn't really work. So later on, people also tried to do that. So for example, Adobe tried that with Flash. Microsoft tried that with Silverlight. So the problem here is that, the good thing is that the engine allows us to provide a much more interactive interface inside the browser. The problem is that the users need to download a particular library for that application to work inside the browser. So that means all these technologies that require something to be installed inside the browser, it's not going to fly with end users. People just don't do that, or they don't like it, and then so we saw that that was not really going to be a success either. So around the year 2005, what happened was that people thought about it, and they said, maybe we should just stick with the web standards that we have. So JavaScript, CSS, HTML, and then this notion of asynchrony was added on top of HTTP, which allowed people to be able to asynchronously go to the server. So that means that in the browser, you don't have to wait for the page to come back. You can just continue doing what you're doing, and whenever the response is back, you can actually update the page very incrementally. So the amount of responsiveness increased dramatically, and this allowed us, web developers, to be able to write applications that were a lot more responsive, a lot more interactive, and they kind of mimicked what people expected or were used to in desktop applications. Right? So in this model, if you look at the server side, it's stateless, and it's basically generating XML or JSON files and sending that to the client side. And the client side now, the browser is doing a lot more. So there's a lot of JavaScript code inside the browser, and it needs to be parsed, needs to be executed. So that means because nowadays everybody has also a very strong client machine, the browser can do a lot more, and it's not only the server that is doing all the work. Right? All right. So this allowed, this enabled the creation of cool applications, web applications like Gmail, Google Docs. So there was a whole new trend of new applications that were built on top of the web. And a lot of different domains started adopting that model. We started seeing things like Cloud9 IDs in the browser. Of course, things like GitHub, Stack Overflow, the things that have really revolutionized how we, as software engineers, we work. And then, of course, all the social media, Facebook, YouTube, Twitter, you name it. Right? So all these famous examples are there as well. So why is this really working? Right? What is the essence of web applications that make them so interesting? So I believe there are basically two things. So one is that you can, because they're based on the standards, you can write the same code and then run it on many different platforms, right? Be it on your mobile application, mobile devices, or your desktop. It doesn't really matter. And it doesn't also really matter which browser you're using, right? So write once, run on anything or anywhere. And the second thing is instantaneous software delivery, right? So every time I have a new update, I commit my changes, I go to my CI, and I deploy. The code is on my server. Basically, that code that is deployed is going to be accessible to all my users. Doesn't really matter how many users I have. So I don't need to, tell my users one by one that they need to do an update or upgrade, right? So anytime there's an update, everybody gets that update. So that's a huge thing in software development, of course, right? So as I mentioned, of course, so these web-based services that also had a really significant impact in terms of how we as software developers also write write and understand code. and also how we interact with each other, of course, right? But of course, we also want to know what software engineering can do for the web. There are a number of technical challenges that the web induces. So it doesn't have only benefits, it also is quite complex, contrary to what a lot of people might think. So these are some of the properties that make web development analysis, web code analysis quite challenging. So at a high level, we are forced to handle or understand different languages, right? So for example, on the client side, you have CSS, JavaScript, the DOM or the HTML. On the server side, you could have any language, like now there's JavaScript or Java, .NET, PHP, you name it, right? So in order for you to analyze one single application, you need to understand maybe 4 or 5 different languages, right? This is very different than when you analyze, for example, a Java desktop application. There's only one language that is doing everything, right? So, and then of course, all these languages, they need to work together. They interact with each other. And this dynamic interaction also induces a whole different layer of complexity, right? On top of that, you have things like there's this distributed nature of the app. There's a client, there's a server. Sometimes you have n-tier architectures, and then of course there is also the async aspect. So there are all these callbacks coming back in different orders, which makes it quite complex to analyze. And of course we have the JavaScript language itself, right? It's an infamous language. A lot of people have written about it. And it has some features or some properties that make it very, very, very difficult to analyze, right? So I've listed a number of them here. I'm not going to talk about all of them, but just to give you an example, the language is dynamically and weakly typed. So anybody who's done static analysis knows that that's a nightmare to deal with, right? It has these features in terms of functions being first-class citizens, so you can pass functions as arguments. The function can have a different number of arguments. You can change the properties of objects at runtime. So it has all these dynamic and kind of weird and difficult properties that make any static analysis that you do unsound. It's very challenging to write static analysis code that does a sound analysis for you, right? And of course, on top of that, again, there are things like eval, for example, which take like a piece of text and they parse and compile that basically at runtime and then execute that piece of text, which again is very difficult to handle. The language is also not compiled, actually, it's interpreted, so that means while programmers write the code, they don't get a lot of feedback in terms of the mistakes that they're making. Okay, so that's just some of the challenges. In terms of achievements, the industry itself, of course, because there's so much interest, has come up with a number of tools for different purposes. So for example, in Green, I have testing tools, so there are things like Selenium, there are unit testing tools like QUnit, Mocha, and then coverage tools like Istanbul, which are quite far already. They're quite robust and useful. There is a bit of static analysis support in terms of Facebook has Flow. There is JS Hint that does a bit of checking in terms of style of the code. And then we have a series of parsers for being able to handle JavaScript code, like Rhino and Eskrima. Also, Google has the Clojure compiler. But at the same time, again, all these tools have limitations because of the challenges I mentioned. And the research in the past, let's say maybe 10 years, has focused on trying to apply some of the traditional techniques, for example, points-to analysis to JavaScript. And so there's static analysis approaches like points-to, data flow analysis, and recently people have also tried to come up with ways to get call graphs and control flow graphs from JavaScript code. But all of these approaches make very simplistic assumptions about the code that they're analyzing. On the dynamic side, dynamic is more precise, but of course it's partial, really depending on how you can execute the program. One very interesting trend which is going to be very useful, I think, is the hybrid approach, in which you combine static and dynamic analysis, which gives you a much, in this particular domain, which gives you much more results. So just to give you an example, this is a call graph that we got from an existing, one of the top static analysis tools. I'm not going to name any names, but one of the best static analysis tools that is available for JavaScript. So this is the static call graph that you get. Now this is the dynamic call graph that you can get just by the existing test cases that the application has. So as you can see, the dynamic call graph is actually larger than the static call graph, which is not what we're used to, right? Like for Java or for any other language, usually the static call graph is a lot bigger than the dynamic call graph, right? And then if you combine these two together, which is what we did for one of our projects, then you can get a nice kind of overlap of these two together so that you get a more complex and more sound model of the application. So that's why I think hybrid analysis is a lot more useful in web applications. So there has been a lot of work on web testing, so that's one of the main domains that has received a lot of attention for web applications. So nowadays we're able to automate to a great extent. We can write crawlers that are able to handle JavaScript. They can generate models. They can generate test cases. There's also some recent work in terms of if you have a lot of test cases, how do you assess the quality of your test cases? And then there's all different sorts of testing types. So for example, cross-browser testing has received a lot of attention in the past maybe 4 or 5 years. Different ways of capturing and replaying. So that's used for test generation as well. And regression testing. So these are some of the main achievements that is out there. And of course, this is not all mine. I'm not talking about my own research a lot here. It's mainly like what we as researchers are doing in this domain. So this is an example of what my group has done. So this is, if you have a set of Selenium test cases that are going through the UI, how good are you, how do you know how good your test cases are, right? So what we proposed was basically, instead of code coverage, let's see if we can measure the state of the page coverage, and then show that to the developers so that they get a sense of how many states and how many transitions are covered. And you can also zoom into a particular state, and then see how many of the actual elements on the page have been covered through your Selenium test cases. All right, so what are some of the future directions? Yeah, so as I mentioned, we still don't really know how to properly infer call graphs or control flow graphs from web code. And again, the main reason, so one is that JavaScript is kind of difficult to handle by itself, but also mainly is because of the interactions between different languages that we have. So this is one direction that has a lot of potential for research. So doing cross-language analysis. We've seen a bit of work in this direction that really is exciting. So there was a paper at FSC 2014, which proposed a program splicing technique by looking at JavaScript and HTML code that is mixed together. And they do a nice data flow analysis in terms of understanding how the data flows through two languages. And this is the type of analysis that we really need for this domain to have effective tools. Another kind of similar work that we did, one of my PhD students did, was looking at all these new frameworks that are coming up, which are called MVC frameworks. So for example, AngularJS, Ember, Backbone, you have all these cool frameworks that abstract away a lot of the details for the developer and make it easier for people to write code. But then even if you look inside those frameworks and how people write code, you see that again there is not a lot of support for developers. So we can make mistakes quite easily there. So we have this technique that automatically goes and tries to find inconsistencies between these different models and views and controllers by looking again at different languages, for example JavaScript and HTML, and see how they should interact and how they are interacting in practice. All right, another area that is that really needs attention is program support in IDEs. So this is IntelliJ, and while you're programming for Java, you get something like this, where you get code completion support, you get refactoring support, and so forth. And if you want to write web code, this is kind of what it feels like. Feels like right now, right? It feels like, for example, VI and 20 years ago, right? Because there is no support. There is a little bit of support, but that's about it, right? And if you're used to, again, IntelliJ and Java programming, you go to write JavaScript code, you can really feel it, right? So I think there's a lot of potential here to be able to provide people with some support. So this is a piece of real code that we took from the web, from GitHub, and if you look at it, there are 3 levels of nesting of callbacks. So we did a large-scale empirical study last year to really try to understand asynchronous callbacks, and we saw that there is an average of 3 levels of nesting, and we saw that some functions even have 8 levels of nesting, which in practice is called the callback hell. So it's very difficult for people to understand this code, right? Of course, you have these anonymous functions, and then these anonymous functions, they do something asynchronously, and then there is the response or the return comes back, and you process that, and you might pass that to another callback, and so forth, right? So being able to handle this and understand it is very difficult. So one project that we have right now is to be able to detect these async callbacks and automatically refactor them to something that is a little bit less problematic. So for example, there's this notion of promises in JavaScript 6, which looks like what you see on the right side. So it's the same functionality, right? But as you can see, the code is quite different. What you have on the right side is a lot more readable and understandable. So, coming up with techniques that can automatically support developers to maybe transition into a more, a better version of JavaScript, I would say. Maybe that's also very useful in the future. A big problem. Every time I talk to a company, this is what they're basically complaining about. Test for agility for web testing, right? So again, if you have civilian test cases, because they're based on element locators, every time there's an update, a lot of test cases break. And this is a huge maintenance cost for people, right? So being able to come up with better locators or better automated repair techniques, this is a very nice area that has a lot of potential for research, I think. Benchmarks. I think somebody else also mentioned this for another domain. Also in web, we're coming up with a lot of tools, techniques, but we don't really compare that much because we don't have, benchmarks or repositories that everybody agrees upon, so that we can actually compare and see how good everyone is doing. So this is definitely an area that we need to pay more attention to. Also empirical studies. So again, most of the techniques people propose nowadays is based on either developer blogs or feelings that people might have about how things should be, or just anecdotal stories. And there isn't a lot of empirical evidence to guide us towards tool building. Of course, this is not unique to web development. All right, another interesting area that we should tap into, I think, as a community, is mining repositories. Of course, this is really for the MSR community, but also if you look at the number of things that are available. So for example, NPM, which is the Node.js package library, has 250K modules right now, right? So that's a lot more than what Maven Central has for Java, for instance, just to give a comparison. And tapping into that, mining it, trying to understand it, is going to be useful in terms of how people write JavaScript code, for example, and what are some of the main challenges. The same is true for GitHub. 3.4 million active projects on GitHub that are using JavaScript. So JavaScript is the #1 language on GitHub right now. Right? Same is true for Stack Overflow. So Stack Overflow did a large-scale study. So they surveyed 26,000 people, developers, and #1 language in terms of popularity turned out to be JavaScript. Right? In 2012, we did a study On Stack Overflow, we tried to understand how, what people complain about, and we saw that back then, around 12% of all the questions were about web development, and that number, I think, it should have increased a lot by now. So, so that's another area that people could look into. Being able to automatically learn from existing artifacts is, I think, also an interesting area. So, for example, one project that we had was to look into existing test cases, make a model of that, and then use an automated tool or test generator to extend the test case around the same areas that the developer thought was interesting to test. And then, of course, you could use machine learning to be able to generate assertions based on, again, programmer-written assertions. So basically, machine learning can be applied here to be able to learn things from a human being, which is already the knowledge that is in the code. So I think that's also another area that could be interesting. Of course, machine learning is going to be it's huge. Almost every paper I read nowadays in software engineering has some sort of machine learning in it, and that kind of scares me too as well. All right, so the last item I have is going from monolithic apps to which are huge apps that do one thing basically as a whole, to microservices, right? So microservices are you basically break up the application into smaller chunks, and this also works in this model in architecture because these microservices themselves, they talk to each other through the REST API, right? So I think being able to understand, analyze, test microservices is going to be huge in the coming years. Of course, JavaScript is everywhere. It's on the client side, server side, also on embedded systems because of its nice event-driven nature. Also for Internet of Things and mobile devices, which have a lot of problems with cross-platform development. If you can come up with proper HTML5 JavaScript techniques, you can mitigate a lot of those problems. So my last slide is this one. So I think because of all the good properties of web applications, instantaneous delivery, also write once, run anywhere, I think any application that can be written as a web application eventually will be. So that's a bold statement, and I'll finish with that. Thanks.
Thank you. Questions? First here.
Okay, thank you for the presentation. What I wanted to ask you is what you think about TypeScript, and if, I don't know, if TypeScript will substitute JavaScript, and what is the adoption by now? Because, for example, Angular 2 already is recommending users to use TypeScript, so I just wanted to ask your opinion.
Yeah, that's a very good question. So I think any solution that has tried to set aside JavaScript and propose a new language or a new way of writing these apps has failed miserably, right? Anytime you try to embrace the language, right, and then maybe provide some extra layers on top of it, just as TypeScript is doing, I think that's going to be a success, right? At the end of the day, TypeScript is compiled to JavaScript, normal JavaScript, standard JavaScript code, right? So personally, I think that's going to be a huge success. Not only TypeScript, anything that is similar. So anything that embraces the language and it doesn't try to replace it.
Hi. So can you contrast and compare Feline's idea of liveness in spreadsheets to liveness in the browser?
Right. Yeah, I think there are already attempts doing that, right? I think because of the dynamic nature of the language, JavaScript, it's quite achievable, it's quite feasible to do that. I don't see any challenges there, to be honest. So because every time you change anything, like some piece of code, the browser is going to dynamically read that, parse that, and then interpret that, and then the page is also updated. So I think that's it's doable, definitely.
And just to respond to that a little bit, I actually use eval. That's how I make the liveness happen in the browser.
Exactly.
I just throw everything you type in that form into an eval. So that horrible feature does make it easier to do some live.
Right, definitely, yeah.
Was there also a question here? Okay. Is that done?
One thing I wanted to get your opinion on was the use of offline apps and the local storage technology.
Right.
It seems like it's quite fragmented in the browser market. And so do you see any challenges there? Because it's sort of a different area, right? Where now you have to look at different types of local storages.
Right.
And things are getting outdated pretty quickly. I think people are talking about service workers now, but I don't know if that's going to hold up or not.
Right. So yeah. So I mean, so so what you're stating is true for not only local storage, inside the browser, or it's actually true for any technology or any language feature that you look for the web. Right. It's evolving very fast. It's changing. There are always different opinions. There's fragmentation. At the same time, there's a lot of solutions available out there to developers, right? And typically the ones that get adopted by the standard, the gods that adopt the standards, those will remain, right? So for the local storage, I'm not quite sure what those people are thinking at the moment, which one is going to be adopted, which technology is going to be adopted. But whatever they choose, at the end of the day, that's what will remain for the coming years.
Hi.
Hi.
So one of the questions I had is, in our university, we teach still everything in terms of Python and Java and Ruby. And
Right.
things like that. But JavaScript is something that they learn on their own, in their own free time. Do you think that if maybe there's more formal education in this, there won't be the callback help?
Yes and no. So some of the code that we're saying, which has these properties like callback help, is actually being written by very skilled developers. So it's not like because they're bad programmers, right? It's just the language itself has these features that enable or that allow people to write such code, right? But I agree. I think seeing the prevalence of this language, I think we should change our teaching and education model a little bit. Maybe we should introduce students to JavaScript a little bit earlier on, right? So I mean, what you're saying, that's exactly what I see in my own classes. I mean, I use Java, just because traditionally that's how it was taught, maybe. But everybody seems to be using JavaScript in my classes. So maybe we, as educators, maybe we also need to change our model of teaching and go with the flow.
Okay, let's thank Ali one more time.